I'm Dr. Himamaheswara Rao, Assistant Professor of Physics, Department of Freshman Engineering, Institute of Aeronautical Engineering, Dundigal, Hyderabad. Welcome to the course titled Atomic and Molecular Spectroscopy. Today we are going to discuss vector atom model, multi-electron atom. In general, Bohr's theory or Sommerfeld theory discussed structure of atom, but they are successful in explaining only single electron atoms such as hydrogen, but they failed to explain about the multi-electron atom. So later on, vector atom model is succeeded to explain multi-electron atoms also. So here, in the case of vector atom model, the main features, the central features of vector atom model are space quantization. One is space quantization, and the second one is electron spin quantization. So these things plays very important key role in explaining all those such as spectral lines, Zeeman effect, anomalous Zeeman effect, Paschen-Bach effect, and Stark effect. So all those things related to structure of atom and electronic configuration are explained by vector atom model. So here the major addition is in this model is vector analysis. So in order to addition of orbital angular momentum, spin angular momentum, all those things are taken by vector analysis. So for example, if there are more than two electrons, if it is only one single electron, if the atom consists of only single electron, there is no problem about finding the total orbital angular momentum or total spin angular momentum. But in case when there are two electrons in single atom, so for example, in that case, if there are more than one electron in an atom, then the total orbital angular momentum should be add up vectorially. Again, it is vectorially. So like that, for total orbital angular momentum, if L1, L2, L3, etc. are individual orbital angular momentum of individual electrons, different electrons. If there are three electrons, for example, if there are only three electrons having individual orbital angular momentum L1, L2, L3, then the total orbital angular momentum of all electrons should be added up. That means L must be equal to L1 plus L2 plus L3. So this addition must be vector addition. So if there are more than three, even for any number of electrons, we should be add like this vectorial addition of orbital angular momentum. So that gives the resultant orbital angular momentum. So for example, let us consider only two electrons. So if L1 is equal to 2, generally the length of this vector indicates the magnitude of the vector. So if L1 equal to 2 and L2 is 1 here, and these orbital angular momentum are oriented in the same direction, then the addition will be like this. If you add these two vectors, so this is the resultant orbital angular momentum, and the total orbital angular momentum is equal to 3. Generally, the representation of orbital angular momentum will be taken in place of will be taken by orbital angular momentum quantum number represented by L. So the total orbital angular momentum or resultant orbital angular momentum L is equal to 3 in this case, in this particular case. But if the orientations are different, for example, the first electron orbital angular momentum is in this direction. So L1 the magnitude also 2. So L1 equal to 2, and for the second electron orbital angular momentum and quantum number 1. So LT is 1, and its orientation is also different. So then the vector addition of these two vectors will be equal to, the magnitude will be equal to 2. So the resultant orbital angular momentum will equal to 2. And again, if the orientation are such that the second vector is anti-parallel to the first vector. So for example, here in the same, for the same vectors L1 equal to 2 and L2 equal to 1, then and the direction or orientation is anti-parallel to the first vector. So here, after addition vectorially, the resultant orbital angular momentum we are getting 1. So there could be orbital angular momentum possible to 3 values. Okay, so it depends on the magnitude and orientation of the orbital angular momentum. So in general, the orbital quantum number L is always an integer. It must be an integer for any atom. So the value of the total orbital quantum number L of the atom must be integer value. So here uh, we can say the addition will be like this. For example, uh, L1 equal to here, in this case particularly L1 equal to 2, L2 equal to 1. You can say that there could be values from L1 plus L2 to L1 minus L2. This could be magnitude. The values, the total values of total orbital angular values momentum values L will be equal to magnitude of L1 plus L2 to magnitude of L1 minus L2. So here in this case L1 equal to 2 and L2 equal to 1, then that means the total all values should be from 2 plus 1 to 2 minus 1. That means 3 to 1 in terms of integral values. 3 to 1, that means 3 to 1. So all orbital angular momenta will be either 3 to 1. So for electron can have values either 3, 2 or 1. So any number uh, can be assigned to the electron. So those only here we are seeing those values. For example, if these values are different, L1 equal to some 3 and L2 equal to 2, then all the orbital angular momenta could be 3 plus 2 to 3 minus 2. That means 5 to 1. That implies all the values could be 5, 4, 3, 2, 1. So the total orbital angular momentum could have values 5, 4, 3, 2 or 1, any number. So different orbital values uh, are possessed by electron. And again, if you want to find the resultant spin angular momentum, similar to the orbital angular momentum, so if there are more than 2 electrons, the vector addition of spin quantum numbers or spin angular momenta of individual electrons like this. So the total spin angular momenta could be taken as summation of individual spin angular momenta of electrons, individual electrons. So if there are two electrons, and again here you must note that the spin quantum number or spin of each electron is equal to 1 by 2. Whatever the electron, the value for spin angular quantum number is always 1 by 2, whatever the electron. But in general, there could be orientations or directions, so it can have plus of or minus of depending on the direction of the spinning of electron. So the spins of different electrons can be either parallel or anti-parallel. If the two electrons are in the same direction, spinning in the same direction, then we say those two electrons are having parallel. And if the two electrons spins are opposite to each other, then those electrons are spinning with anti-parallel directions. So if the atom has an even number of electrons, so for example, we will see there are two electrons having each one having 1 by 2, 1 by 2, the resultant spin angular momentum, the length also increases like this. This is s1 equal to half, s2 equal to half. The resultant spin angular momentum s could be taken as 1 by 2 plus 1 by 2. So here it is 1. If the two spins, if these two spins are parallel, in this case, if the spins are parallel, if the spins are anti-parallel, one is up and one is down. So here also is S1 equal to half, S2 equal to half, but uh, but here in this case the total spin angular momenta will be equal to 0 as the two spins are anti-parallel. If we consider three electrons, in the case of three electrons, the spins, two spins could be parallel, S1 equal to 1 by 2, S2 equal to 1 by 2, and S3 equal to 1 by 2, then the total spin quantum number, the total spin can be S equal to total, that means resultant spin quantum number S equal to 3 by 2. And again, if there are two spins with same direction and one is maybe anti-parallel, opposite direction. Here it is S1 equal to half, S2 equal to half, and S3 equal to half. For any number of electrons, the spin is having same value 1 by 2. But the resultant value, here only one electron is in the anti-parallel direction to the remaining two electrons, so that the resultant, the resultant, the resultant spin angular momentum S equal to 1 by 2. So when there are three electrons, the total spin angular momenta could have the values. One is 1 by 2 or 3 by 2. There could be two values, possible values for total spin angular momenta. So there are two electrons. So we can say from this observation, we can say that if there are, when here we mentioned already, if the atom has an even number of electrons, 2, 4, 6, then the value of S can be either zero here. If there are two electrons, one is upside and the second one is downside, the total spin quantum number is equal to 0. And if the two electrons are in the same direction, having same orientation, same spin, then the total spin quantum number is equal to 1. In the same way, if there are 4 electrons, odd number, that means odd number of electrons, 4 electrons, the total spin quantum number could be having values uh, 2, 1, 0, either 0 or uh, even integer value. So for any number of electrons having even number of electrons, the total spin quantum number S can have either 0 or an integer value. And again, if the atom has an odd number of electrons, it will be half odd integer, in this case. For example, if there are three electrons, we can see here that total spin quantum number S is equal to either half or 3 weight, depending on the orientation of the electrons. There are 3 electrons, so depending on the orientations of electrons, the total spin quantum number can have values either 1 by 2 or 3 by 2. If 3 electrons are in the same direction, that means maybe all are in the up direction or even for down direction also. If there are 3 electrons which are with spin down, then also the total spin quantum number is equal to 3 by 2. So if the 3 electrons are in the same direction spin, then the total spin quantum number is equal to 3 by 2. But when 2 electrons are in the same direction and the remaining 1 electron is in the opposite direction, the total spin quantum number is equal to 1 by 2. Even the 2 electrons are in the down direction and is opposite to this direction, up, the total spin quantum number is equal to 1 by 2. So that when there are 3 electrons, the total spin quantum number can have values either 1 by 2 or 3 by 2, two possible values. Okay, so if there are 4 electrons, we already discussed it in the earlier slide, 2 and 0. If there are 4 electrons, okay, so S can have values 2, 1, 0. And if there are 5 electrons, then we can easily show that the total spin quantum number can have values 5 by 2, 3 by 2, 1 by 2. So we can say that if there are odd number of electrons in any atom, the total spin quantum number can have values of odd integers, odd of integer values like 5 by 2, 3 by 2, 1 by 2. If there are again 6 electrons, then the total spin quantum number can have 3, 2, 1, 0, depending on the orientation of spin of the electrons inside the atom, in any atom. So if there are 7 electrons, then S can have 7 by 2, 5 by 2, 3 by 2, 1 by 2, such values. And again, let us discuss coupling schemes. If there are more than 2 electrons in any atom, each electron has several quantum numbers to describe the motion of the electron. So, as we discussed in the earlier lecture, for every electron in the atom, it can have 7 quantum numbers. So, all these quantum numbers are useful to describe the motion of the electron, in which orbital or in which orientation the orbit is taking place, or what is the direction of electron, so what is the position. So all these things are described by using those quantum numbers. So then each atom has its way in which the different vectors of the electrons may combine. So again, all these uh, quantum numbers are also expressed in terms of vectors. For example, azimuthal quantum number is very important to describe the motion of the electron. Uh, and again, orbital quantum number, orbital angular momenta, and all these are important to describe the motion of the electron. So again, here, when there are more than one electron, when there are more than one electron, then the complexity comes. The total orbital angular momentum of the entire atom changes. If there is only one electron, so there is no problem about finding the total orbital angular momentum, because only one electron is orbiting in the single uh, orbit. But in the case when there are two electrons or more than two electrons, that means more than one electron, then one electron can have separate orbital angular momentum. The second electron can have other orbital angular momentum. Then the total orbital angular momentum changes depending on the orientation and spinning of electron. All those things come into the picture whenever we need to describe about the condition of the state of the atom. So state of each electron has to be described. So, but whenever we have the individual vectors for each and every electron, we can take different ways. There are different ways to represent the state of electron or state of the atom also, by combining these what we call interaction, depending on the interaction of electrons or depending on the coupling. Maybe simply we can say the coupling between the electrons inside the atom. Based on this coupling, we can describe about the state of the atom. So these are can be taken by using the component vectors, whatever we say about the quantum numbers. So component vectors can plays very important role in describing about the state of electron and state of the atom also. So since the orbital and spin motions of the electron produce magnetic fields, in general, when the electron is revolving around the nucleus in certain orbit, then uh, it also produces magnetic field, because as the electron is revolving, it seems like a loop. Uh, that means current is circulating in the loop. That means it can produce the magnetic field. So either it is in the orbital motion or spin motion, the electron produces the magnetic field throughout its motion. So it results in mutual. There could be mutual perturbations. So based on the value or magnitude of the orbital angular momentum or spin angular momentum, there could be different mutual perturbations. Generally, these perturbations are what we say coupling can be distinguished in two types. These are the general types. Maybe there could be several other types also, but more popular coupling schemes are two types. One is known as LS coupling, and the second one is JZ coupling. There are two coupling schemes which are very important, which are very general. Those two are LS coupling and JZ coupling. So let us discuss about LS coupling. It is also known as Russell-Saunders coupling. It is the most frequently occurring coupling. It is the most frequently occurring coupling in most of the atoms. So it is known as normal coupling. It is also known as normal coupling because it occurs most frequently in the atoms. So in this, all the spin vectors of the electrons combine to form total spin angular momentum S, and all the orbital angular momenta will be added up to form the resultant orbital angular momentum vector L. So that means if there are more than one electron, we need to add up individual spin angular momentum quantum numbers to give the total spin angular momentum quantum number. And in the same way, uh, individual electron orbital angular momentum quantum numbers to be added to give the total orbital angular momentum quantum number L. So we obtain total resultant spin angular momentum quantum number and resultant orbital angular momentum quantum number, and then we combine these two resultant vectors to give the total angular momentum quantum number J. So after adding these two quantum numbers, we will get a total angular quantum number J, J of the atom. So resultant angular total resultant angular momentum could be obtained by adding the individual total spin angular momentum and orbital angular momentum. So in this scheme, for obtaining the total angular quantum number, we add up individual orbital angular momenta of individual electrons, and for obtaining the total spin quantum number of all electrons, we need to add individual electron spin quantum numbers like this, and then the two vectors will be added up to give total angular quantum number, total angular quantum number of the particular atom. So this scheme is called LS coupling. This scheme is called LS coupling. So this sort of coupling is the most natural one occurring in most of the atoms, and when the interaction between the individual spins on the one hand and the individual orbital moment of the electrons on the other hand are very strong. This coupling occurs when individual electron spin quantum numbers are very strong, and again individual orbital angular momentum quantum numbers are very strong. Then this particular coupling occurs inside the atom. So that means individual electrons support for the addition of all the spins of individual electrons individually to add up the particular spin quantum number for the total spin quantum number for the atom, and also individual orbital angular momenta add up to give the total orbital angular momenta, and then the total angular momentum will be given by adding the individual total spin quantum number or total quantum number. So on this here we can express this scheme by vector method also. For example, if there are two spins like this, this is the spin S1 and this is spin S2, the resultant vector S could be given like this, the resultant vector. And if there are orbital angular momenta L1 and L2, the resultant orbital angular momenta L could be like this. So adding of individual orbital angular momenta gives total orbital angular momenta. And then total angular momenta can be given by adding up this total spin quantum number and total orbital quantum number. So maybe like this. So adding of S and L gives the total orbital angular moment, total angular momentum quantum number J. The same way we can express the vector method for 3, 4 electrons also. There are 3 electrons. 3 electrons, uh, the spin quantum number can have values like this. If there are 3 electrons, the spin quantum number of 3 electrons can be like this. The resultant may be like this. The resultant spin quantum number S1, S2, S3. And similarly, the orbital angular momenta quantum numbers for individual electrons, if there are 3 electrons, are equal to L1, L2, L3 individually. So that the resultant orbital angular momentum after adding all these 3 quantum numbers L1, L2, L3, we may get L. Then the addition of total spin quantum number and orbital angular momentum can give the total angular momentum quantum J. So this is the vector notation of addition of the spin quantum number and orbital angular momentum quantum number in LS coupling. So LS coupling is governed mainly, this scheme is governed by mainly these principles. What those principles are, all the 3 vectors, L, S and J are quantized. So these are the basic principles followed by LS coupling. So these values L, S and J are quantized values. And again L is always integer. Whatever the number of electrons present in the atom, L is always an integer. It may take values 0, either 0 also, including 0, 1, 2, 3, etc. Any integer. S is an integer. The quantum number, spin quantum number S is an integer or half integer, depending on the number of electrons. So depending particularly the spin quantum number depends on the number of electrons, total spin quantum number. So it depends on the number of electrons. If there are odd number of electrons, the total spin quantum number could have half odd integer values. So thus for an atom containing a single electron, S can have only value 1 by 2. For a 2 electron system, S may have either 0 or 1 depending on whether the spin vectors are parallel or anti-parallel. As we discussed in the earlier slides, if there are even number of electrons present in the atom, then we can have values 0, 1, 2, 3 like integer values. For odd number of electrons in an atom, we can have half odd integer values like 5 by 2, 3 by 2, 1 by 2. Okay. And the fourth point is J, total angular momentum quantum number J, the vector sum of L and S. J is represented by the total addition of vector sum of L and S. That means orbital angular momentum and spin angular momentum. So it is also must be integer like 0, 1, 2, 3 for odd electron system. Integer 0, 1, 2, 3. And for even electron system, there are even number of electrons. The value of J must be equal to 1 by 2, 3 by 2, 5 by 2. So any number of integer values. So in general, the possible number of values which J can have are will be 2s plus 1 if L is greater than S. That means S is smaller value, then there could be 2s plus 1 values for J. For example, mm, L equal to 2 and S is equal to half. Then there could be L equal to 2 here. So there could be 2 plus half. No, no. So there could be 2s plus 1 values as S is smaller here in this case. So 2s plus 1 means 2 into 1 by 2 plus 1. That means there could be two values for J. Actually, there could be J values could be taken from magnitude of L plus S to L minus S, so that here L plus S means 2 plus of 2, the total values in terms of integers could have up to in steps of 1, unit 1, so 2 minus of, so this is 5 by 2 and 3 by 2. So there could have only two values. If there are values like 2 and half, so as we said, according to the formula, there could be values for J. One is 5 by 2 and another one is 3 by 2. There could be only two values. Okay. So and again, this is the formula when L is smaller than S. So the quantity 2s plus 1 is called multiplicity of the L. Multiplicity of the L state. It gives the permitted values of J for a given value of L. For any given number L, the value 2s plus 1 gives the permitted states or values of L for the electron. J is always positive since it represents the total angular momentum. J always represents the positive value because it represents the total angular momentum of the atom. So in case of JJ coupling, the second one is the JJ coupling. This coupling is found when the interaction between the spin and orbital angular momentum vectors of each electron individually is stronger than that between either the spin vectors or orbital angular momentum vectors individually for different electrons. So if there are more than one electron, 2, 3 or 5 electrons. So here in the case of JJ coupling, that means JJ coupling is applied only when the individual spin and orbital angular momentum are stronger to add up for individual electrons, then it takes place. So in such case, each electron is considered separately. Each electron is considered separately. That means for each electron there could have spin angular momentum and orbital angular momentum. So as they are stronger to add up there itself individually, so the total angular momentum could be added by taking spin angular momentum quantum number and orbital angular quantum number. So the total angular momentum of the particular electron J could be taken as by adding the spin and orbital angular quantum number L plus S. So then we take total angular momentum for all electrons and then add up to give the total angular momentum of entire atom. So the total angular momentum J of the atom is obtained by taking the vector sum of all individual J vectors of different electrons. This coupling scheme may be symbolically represented as Ji equal to Li plus Sa, where J equal to summation of J. So individual electron are total angular momenta will be added, and then all individual total angular momenta are added to give the total angular momenta of entire electron. So this type of coupling exists mainly in heavy atoms. This type of scheme is applied for heavier atoms. Here in this case, if there are two electrons, particularly if this is the spin S1 for one electron, and this is L1 for the same electron, orbital angular momentum S2, L2, this is the S2 and L2. So here the total uh, angular momentum, this is the L1, will be taken by adding up these individual spin quantum number and orbital quantum number. This is the J1. And here also for the second electron, spin angular momentum. This is the orbital angular momentum. Total angular momenta will be taken by adding these two vectors. So for the second electron, the total angular momenta can be calculated as J2. And now after adding these individual total angular momenta, now we will take the total angular momenta of the atom by taking individual angular momenta of individual electrons. So this is the J, that is equal to J1 plus J2. So this is the vectorial notation of JJ coupling. So with this we discussed the coupling schemes particularly in this session. Okay, so with this, these are the reference books. So uh, these are the textbooks for reference. So thank you all.
Like, share, and subscribe. Hit the bell icon for more updates.